So one second to remove the okay. Yeah, so first I would like to formally thank Dr. Parakrama Ekanaik and Dr. Roshan Godaliadda and all the other faculty members who invited us to conduct this workshop. Many thanks also go out to Praveen Sandalu, Chatami, and all the others who participated in organizing this event. We are honored to be invited. So it has been like 15 years since I graduated from University of Peradeniya, so it's nice to be back, although it's virtually. And Shehan, do you like to add some words?
Sure. Thank you, Dr. Ekanaik and Dr. Godaliadda for inviting us, and thanks all the members of EASE who are behind organizing this one. And thank you, Chatmi and Praveen, for the nice introduction. We are really happy to be here. So we will conduct the session as like slideshow, but if you have any questions, please feel free to stop us and ask any questions. At the end, I invite like all the students to be interactive and like ask any questions. No question is a stupid question, right? So if you have any questions, don't hesitate to ask it.
Okay.
Right. Oh, one more thing, Indika. So in this presentation, you see like two other names. So apart from Indika's and mine, so Sushan is our supervisor. So she's the supervisor of our team. Our team name happens to be a model-based calibration optimization team at Ford Motor Company. And Ben Nolt is our manager. So usually when we do an external presentation, so we include those names. So that's why you see like 4 names on the presentation.
Okay. Thanks, Shehan. So I actually quickly added these 2 pictures after Roshan's what Roshan mentioned about my career path. Anyhow, so I graduated from University of Peradeniya, Department of Electrical and Electronic Engineering in 2007. There, I focused my study there on controls and robotics and controls. Then after that, I actually decided to pursue a PhD in applied mathematics at Texas Tech University in Lubbock, Texas. But although it's applied mathematics, it's my research study was still on control techniques, specifically control techniques pertaining to biomechanical systems. So after the PhD in applied mathematics, I actually went to a robotics lab, again in the electrical engineering department of University of Texas at Arlington. So why I went there first was to actually to work on the control techniques that I studied under my PhD, to apply those on a real android in the sense a humanoid robot. So these are 2 of the robots that I worked with. I got the chance to work with many other robots, but the more human-like robot in the lower corner is named Philip K. Dick. It's that's the name of an actual science fiction writer, and that robot has like strings attached to different parts of its skin, so it can make facial expressions. It can move its eyes. So I applied the control techniques, algorithms that I studied during my PhD on this humanoid robot. Yeah, so in that lab, I mainly studied social robotics and human-machine interfaces. So most of my publications are in those fields. Then after that, I decided to join Ford Motor Company. That was in 2019. So yeah, you'll see the commonality of what I'm doing, some of the commonality of what I'm doing now with the career path I have taken, although it has been from engineering to applied mathematics back into robotics and automotive industry. There's still a lot of commonality there. You'll see more of that in later slides as we progress through the presentation. So I'll ask Shehan, do you want to introduce yourself?
Sure, Dr. Wijayasinghe, thank you. So I graduated from mechanical engineering department in 2008. So then I worked in the industry for 3 years. So then I decided to pursue higher studies. I came to Texas Tech in 2011, and that's where like Dr. Ekanayaka, Dr. Wijayasinghe like were with me during that time. So I finished my PhD in mechanical engineering in 2015. So my main focus was alternative power sources for automobile application. So my main research focused on how to use ammonia for cars. So that's my PhD research. After that, I worked there, I joined the academic career path as a postdoctoral research fellow in the same university. And I was there for like briefly 8 months. And then I decided to join the industry. So as always, I have wanted to join like automotive industry. So I joined the Ford Motor Company in 2016, still in the electrified powertrain department as a model-based calibration optimization engineer. So when you are in the industry for a long time, usually in the academia, you publish papers to disseminate your knowledge. But in the industry, it's all like funded by one company. So what you do is like you publish patents. So I have 3 granted and 3 published patents. And also like I have 12 pending patents, both international and in US. They are all about XEVs. XEVs stands for electrified vehicles for autonomous vehicles. So those are like my patents on, and also like I have numerous academic publications. So Dr. Wijayasinghe, I think we can discuss in the informal session if students have any questions about our career path. So we can begin the presentation now, right?
Yeah, thank you. So, so automotive industry is facing unique challenges these days. So it's undergoing a transformation. So back in the day, mostly when you think about a car or a vehicle, it's mostly mechanical designs, right? But more and more, they're incorporating more electronics and software, and basically vehicles are gradually becoming robots. So if you think of an autonomous vehicle, that would be a robot. So these transformations bring advantages and challenges. To talk about one challenge, these systems are very complex. So if you think about this F-150 pickup truck, that has 150 million lines of code controlling that. So they're very complex. They bring unique challenges, but also those bring advantages. So these complexities actually bring more versatility to the vehicle. There are many tunable parameters. So that allows that to have more advanced controls. And also these like incorporating software and electronics give it the possibility to implement features which weren't possible before without them. So, but another challenge that is like kind of unforeseen, but something that came up with COVID is I don't know whether any of you have read about the chip shortage. So, so now vehicles incorporating more and more tech, we have to fight with consumer electronics manufacturers for important computer chips. So that is a real challenge facing all automotive manufacturers are facing. So yeah, so Shehan, do you have anything to add there?
Sure, those are the few challenges and as well as opportunities, I would say. So then going beyond that, now we try to make our cars self-driving or autonomous. So there's big initiative with automotive manufacturers in US, and not in only US, it could be Europe or Japan, all over the world, to develop the first level 5 capable self-driving cars. So there's a big competition going on there. So with that, the automotive landscape is changing. I would say with the autonomous vehicle, definitely you would not have a car to own, which means you can't, I mean, it's really expensive, with all these technologies and complexities, the cars becoming very expensive. You would, if you are a wealthy person, you can own the car, but still car manufacturers would not give you to buy it. So you have to go into some other aspects called ride sharing. This autonomous vehicle will mostly be used in ride sharing. In fact, that is something the Uber and Lyft are doing, or in Sri Lanka, I would say Pick Me. So people are moving towards from car ownership to ride sharing landscape, especially with the younger generation. So they like to rent things, and then they don't like to own things. They don't like the hassle of owning things and keeping on maintaining the vehicles and all these kind of things. So with that, our customer landscape changed, and we have to study that part too. So we have to make our product according to this ever changing and ever evolving customer landscape and the global demand. So those are the few challenges that when we look at, as an automotive manufacturer, when we look at product development, we have to consider everything. So as Indika mentioned, the Ford F-150 now have 150 million lines of code. It's because the product is complex. Earlier, it had only an engine, right? So that's what it had, and then it has all the mechanical parts. But right now, it has so many electrified components. It has a battery, it has motors, and then it has motor generators. And these things are becoming complex. So that's why the control strategy or the control code is becoming complex. And we need multidisciplinary engineers working on the same product. So as you can see, so my background and Indika's background, it's different, but still we are working on the same team, on same products, and developing same things. Indika, you can go forward, I think.
Thank you. Yeah, so we proceed, we would like to mention that the views and opinions expressed in this presentation are those of the presenters, that is us, and do not necessarily reflect the official policy or position of Ford Motor Company. And also, we would like to just mention some of the abbreviations that we'll be using in this presentation. So CAE is computer-aided engineering. AI would be artificial intelligence. ML is machine learning. HPC would be high-performance computing clusters. And MBCO is model-based calibration optimization. So what that really means, the last one, the model-based calibration optimization, we'll go into the details of what that really means later in the presentation. So let me also, to save the bandwidth, give me 1 second. Okay. So then we'll try to address why we use computer-aided engineering and machine learning in automotive products and in automotive product development. So some of the usages of machine learning and machine learning especially is something that the end user can see. For instance, if you look at features that are being added to new vehicles, autonomous driving, and even just like the phone, if the vehicle, when the vehicle can understand voice commands. All those are implemented with the machine learning algorithms, right? So that is something the end user can see. But there are also things that happen in the background that the end user doesn't see. This happens during the product development. So, so back in the day, it's even to produce the exterior design of the vehicle, somebody would have to start with a clay model, right? Even now, people still use clay models, but we don't start there. Like we have CAD software to design these components, right? So designing those in a CAD software is one aspect of it, but most importantly, we can evaluate different attributes of these components long before any physical component is ever built. So back in the day, if you want to see how a vehicle would, how comfortable a vehicle would be, and what's the like how it would survive a crash, you would have to build the vehicle and test it, right? That's expensive and time consuming. But with simulations, we know that we can simulate all these things, and that we can do that long before actual components are built. So that saves time and cost during the product development. And also, even more importantly, this gives us the ability to utilize optimization algorithms in product design, because, give me 1 second. So it allows us to use optimization algorithms in product design, which is not possible without the aid of computers, right? You need to have a lot of data points coming from different parameters of the design. So these are some of the reasons why we use computer-aided engineering in automotive product development. So, so what I'm going to do is I'm going to talk about some examples of the usage of computer-aided engineering and machine learning here. I'm going to go over 3 of them in kind of general details. And then Dr. Haputhanthri will go over one of these, actually the first item here, in depth in the latter part of the presentation. So the first one is something that our team does in a regular basis. The other 3, like we don't work on autonomous driving applications. Our team doesn't. But like I'm going to give a brief description about components and how they work in one slide. And I'll do the same for the 2 items. So, so these are like the main components of autonomous driving, implementing autonomous driving. And those are perception, localization, planning, and control. So actually, I'm going to go back to one thing that I mentioned like in an earlier slide, that is vehicles are gradually becoming robots. And if you go into robotics, these are exactly the same components that a robot would use to navigate through a building per se. So the only difference I see is like when you talk about these 4 things for robots, for the localization, usually it's localization and mapping, because a robot is usually we expect the robot to even go into uncharted territory and self-map the unknown areas. So it keeps on expanding its map. So that's what, so I'll get into that details a little bit later. But in a vehicle, most of the autonomous driving software, like those do the mapping before the car is delivered to the customers. So we don't have the mapping part directly in here, although somebody has to do the mapping. So out of these 4 areas, perception and planning are 2 areas that use deep learning a lot. We all know that perception or image processing, there are traditional algorithms, but like they have been using deep learning algorithms for a while. And when you go to planning, again, there are like traditional algorithms like what I have listed here, the A-star algorithm, and yeah, so there are traditional algorithms, but more and more people are using deep learning algorithms, in this case, deep reinforcement learning. So if I briefly talk about reinforcement learning, because I'm going to use the name reinforcement learning later in the presentation also. So this is a field that is studied a lot for robotics also. So reinforcement learning is trying to imitate how a biological entity learns. So what usually we learn by first exploring, and then depending on how what the reaction we get from the environment, like it could be a positive reaction, in which case we call it a reward, a positive reward or a negative reward. So based on whether it's a positive or negative reward, we adjust our actions going forward, right? So reinforcement learning is trying to imitate that in robotics. So it goes through an exploration and exploitation. Those are the 2 things that it does. So it first randomly explore, and depending on the reward, it adjusts its policy so that the actions it takes, it learns to take actions that maximizes the future reward. So it gradually learns how to do, how to take correct actions. So that's a field in robotics that's heavily now used in planning. So then when we get to localization, it's mostly traditional algorithms that are used now, but there are deep learning algorithms that are coming up for those as well. And then when we talk about controls, again, we mostly think about traditional algorithms, right? But there are studies going on for what's called end-to-end learning. Again, trying to kind of imitate how like our brains work. Like end-to-end learning is you connect the sensors to a neural network, and outputs are the actions, actuator outputs. So everything in between the sensors and actuators are learned. So that's another emerging field. So people are trying that end-to-end learning for controls. So that's one machine learning approach for controls. Okay. So this is something that our team also sometimes have to do. So when you think about modeling, say, a vehicle, so one can think that we start with the first principles. The first principles are the physics equations, right? So one can think that we start with the first principles and build the whole vehicle, and then try to use that. But like modeling everything with first principles, sometimes it's impossible, and sometimes it's even if it's possible, we prefer not to do it. The reasons are so sometimes the systems are too complex that it might take a lot of time and like time to develop these models. And the second reason would be the simulation time. So sometimes, for instance, models of engines that simulate all the even the gas compressions and all those things, but those take like hours to simulate a few seconds of the simulation. That's not feasible for simulating a whole vehicle running like 40-50 mile trails, right? So we want to improve the simulation time. So so due to those reasons, sometimes we need to simplify the model so that it runs faster. Also, because then we can model some of the components faster. So the one simplest thing that we can do would be to have a lookup table. But a lookup table, if you think about a lookup table, just inputs and outputs, it cannot model dynamics, right? So if we are only interested in the steady state behavior of a system, a lookup table would do. But if you want to model a dynamic system, if you want to approximate a dynamic system with data, then recurrent neural networks is something we can use. So for this, we need to train a neural network. So we need to have some data of inputs and outputs to the system. Then we train the recurrent neural network. So these recurrent neural networks do have internal feedback loops. So they can actually model dynamics as opposed to a simple neural network, which cannot do that. So, and these are the same neural networks that are used for like voice recognition and all, because they can model dynamics. So there are some pros and cons. Some of the cons are you need a lot of data to properly model, properly cover all input space of a dynamic system. So, and if there's a problem, if you detect a problem, it's hard to debug. You might have to retrain the whole neural network. And then okay, so most of our applications require that we simulate a vehicle in a closed loop manner. That is, we wanted to like follow a speed trace. So simulating that vehicle means that we also have to simulate the environment, but also we need to model the driver behavior also. So modeling the driver could be as simple as a PID controller. But if you want to, I mean, like if you want to compare it with the real test data, we need to have the driver modeled as close as possible to the behavior of an actual driver. So in such a situation, we might have to use some machine learning. So these are things that people are researching. So one such method is inverse reinforcement learning. I talked about reinforcement learning before. That is, an agent is trying to learn how to take correct actions. But in inverse reinforcement learning, we do the opposite. That is, we observe an agent, we observe an actual driver, we get the data, and we try to use the reinforcement learning techniques to learn what the agent does. and what the environment does, what objectives the agent is trying to achieve, and what rewards the environment is providing the agent. So we learn the agent's behavior through inverse reinforcement learning. So the rest of the presentation is about how our team got to where we are and what we are doing at Ford. Those include challenges we faced, and Ford's push to CAE models, and our part in that story, our team's part in that story. So these are again some of the challenges. Some of these things we discussed earlier. Controllers in today's vehicles are very complex. There are many control modules, many functionalities, and they result in thousands of control parameters. So in a PID controller, you know that there are three parameters that we can tune, right? So, but in these control algorithms, there are like thousands of parameters. So when we talk about calibration, what we mean is controller parameter tuning. So we want to tune these parameters to achieve the desired attributes of the vehicle. And there are like stringent regulations in US in terms of like emissions, crash testing, crash worthiness, all these aspects. And these regulations also change from market to market. The regulations in US is not the same as in Europe or China. So, and also we need to compete with the competitors in metrics that matter to the consumers. And we also want to like do these things with the minimal development cost and time. And another very important aspect is optimizing vehicles for different attributes. That's maybe something that our team does. So what we mean is, I'll explain it with these two vehicles. So here we have a Ford Focus EcoBoost hybrid and a Ford F-150 Power Boost hybrid. Those are both are hybrid systems, but we optimize these vehicles for different attributes. For the car, what we are interested in is like the attributes we are interested in are fuel economy and drivability. But for the pickup truck, we are more interested in the power output and fuel economy. And so we have to tune different vehicles for to achieve different attributes. And even for the same vehicle, nowadays you have different modes. So even for the same vehicle, sometimes you have to tune the same vehicles to achieve different characteristics depending on the mode you are in. So this is our journey towards computer-aided engineering. So traditionally, how we do this is we have a prototype. We have prototype vehicles, and we have hundreds of them per design, and calibration engineers get into these vehicles and drive around in roads and on dynos, and from those data we calibrate the vehicles. But this is expensive, as you can see. We need hundreds of vehicles, and each of these vehicles like these cost more than a production car, because these are you produce this in you custom design these at this stage, in the pre-production stage. So test mills, as we call them, cost like $500,000 per vehicle. So this is very expensive. So we would like to, and it also takes a lot of time to do this. So we would like to minimize this cost and time. So the next step of that would be to strip the outer shell and use a power systems dyno. Even that is not getting reducing the cost significantly. And the next step would be hardware in the loop. In that, we model the plant, or that is the vehicle, in a real-time system, computer system, and the real hardware is the controller. So part of the system is hardware, part of the system is software. And then the next stage, which is where we want to go, is CAE models that you can run in a computer. So the controller is also now in the computer. So this allows us to run like many different simulations, even simultaneously, depending on the computer resources. So we can generate a lot of data. And we can also, in addition to reducing the cost and time, we can also use many analytical tools to based on this large data set that we collect. So when you assemble a real vehicle, how we do that is we have different engines, different components like engine, controllers, high voltage batteries, transmissions. So we then take those components and assemble them into a vehicle in a factory. So in the CAE approach, we try to follow the same kind of process. We try to we build component libraries, and then we have also in this slide you can see SysML. That's a modeling language. So with that we can create like an abstract model of a vehicle. Then we use the autonomy software to populate those components in the abstract model, abstract architecture. So SysML creates the architecture. In autonomy, we populate those components in the architecture, and autonomy assembles that into one single vehicle. So we have software components, we have abstract architecture, and we use another software to combine the abstract architecture, populate them with actual components, and build a vehicle. That is the CAE model. So now I will ask Dr. Haputhanthri to take the present the slides from.
Sure. Thank you, Indika. Thank you, Dr. Wijayasinghe. So Indika explained how we build a CAE model. So in this picture, you see what a CAE model is, right? So when we talk about the CAE model, so we call it EVV, Electrified Virtual Vehicle, or Digital Twin. So the digital twin is like a twin to your actual vehicle. So this vehicle is supposed to behave like a prototype or the test muse that Indika described. This has like several components. The first one is your plant model at the very bottom of the picture. That's where you model your all hardware components. It could be your battery, it could be your engine, or it could be your transmission, or whatever it is. First, we build a very representative CAE model for your physics or like physical components. Then there comes the software or the control systems. So that is the like on the right top corner of the picture. So you have the actual software code which controls these components. For example, your motor has to be controlled by a motor controller. So there's a controller for that. In a typical vehicle, in today's world, you have like 18 different controllers. So they're not microcontrollers, like they are full-fledged electrical control units. We call them ECUs. There are roughly about 18 ECUs in a car. That's a like very low-end number. So other cars might have more than that. So we bring in those controllers or the software code into the model. So Indika used a specific term called SIL, or software in loop. So that's, we bring in them as like a software in loop components. And then Indika explained how we integrate the driver and the environment. So when we put together all these components, it's called a CAE model. In our terms, it's called the electrified virtual vehicle. So today we are going to focus about the control system. The control system is essentially the mind of the vehicle, right? So it's same as like our physical body. For example, I always use this chalk during this talk. So in certain days or like certain time of the year, I think that like I want to have like 6-pack abs, right? So it's very easy to change my mind, but it's very hard for me to go to the gym and actually do the exercises and go to the routine to build that up. So it's very hard to change my physical body, but it's very easy for me to change my mind. So it's same for the vehicle. So when we are in the product development, if I want to change a hardware component, like the engine, so that's very, very expensive. It's like because we develop millions of these vehicles, right? So if you want to change the engine, now we have to go back and rewrite the entire supply chain. So we have to select a supplier and we have to like vet them and go all these routes, which is like really, really expensive. So it could be in like in terms of like millions of dollars, right? In monetary value. But that's why we have the control systems, which is easy to change. So almost like all the automotive manufacturers develop their control systems in-house, which means like they develop the control system within their organization. And on top of these control systems, we have parameter tuning or tunable parameters. We call them calibrations. So in a typical vehicle, we have 10,000 plus calibration variables or tunable parameters. So they could be varying from scalars or the two-dimensional or three-dimensional calibration tables. So think about it. So when we are talking about the combination and the permutations, there could be millions of combinations of these tunable parameters. So these parameters together define the character of a vehicle. So, in Ford terminology, we have Ford Mustangs and like then we have Ford Escape or Ford F-150. So we use these calibration variables to define the character of the vehicle. So that is how, when you drive the vehicle, this is what you feel actually. So if you drive a Mustang, it's intended to be like really fast. And we tune the Mustang to be really fast using these calibration variables. That's how we do that. And right now we talk about like few like buzzwords like calibration variables, calibration tables, and calibrate. So now let's look at what actually a calibration is in simple terms. So this is like introduction to calibration. This is calibration 101. So this is a simple PID controller. Indika explained it at the very beginning. So in a PID controller, so you have 3 parameters to tune. You are like PID gains, right? So you can use a manual tuning and Siegler-Nicholas method or like relay method or whatever the method that you use. You have like one objective. So you have to get the behavior of the controller to the ideal curve, which is the green line. So if you don't tune them properly, either you will overshoot or undershoot them, right? So the whole purpose of tuning these calibration parameters or like tunable parameters is to achieve that ideal curve. So when we go to the calibration optimization, so the calibration of actual vehicle, it is nothing other than that. So the scale is large, right? So you are changing 10,000 plus or like millions of combinations of calibration variables, but you change those calibration variables to achieve a defined character of the vehicle. So that's what we do in the calibration optimization. So now I would introduce a word, actually we talk about it like the model-based calibration optimization. So now we talk about the calibration optimization and then we talk about the models or the CAE models. So my team at Ford Motor Company is called model-based calibration optimization because we use CAE models to optimize this calibration. And that's how this name came into existence. Indika, we can go to the next slide. Okay, now I'm going to introduce you some of the like, Indika talked about 4 examples at the very beginning, how we used machine learning for the in automotive industry. And he discussed about three of them in very brief terminology or like any very nutshell. So the first one that he mentioned is the calibration optimization. So this is what we do on daily basis. and we decided to include few slides to explain you the process in detail. So in this one, you can see at the very middle, we have the calibration tables. So we want to change these calibration tables, as we discussed. They are like tunable parameters to achieve a certain objective. So it could be the fuel economy, or it could be like comfortability, or it could be performance, right? So when we talk about the fuel economy, you know, like we need to have the highest miles per gallon, or like kilometers per liter per car. So that's a fuel economy. So when you talk about performance, so we need to have like 0 to 100 kph, like 0 to 100 time. We want to get that speed in a like quickest time as possible. You think like, okay, they are like competing objectives. When we tune the car to be fast, so it's not going to be fuel efficient, right? So we have to think about all these aspects. So that's the beauty of product development. So you can't just think about one aspect or one attributes. You have to like optimize them. You can't maximize one objective, which is like if you maximize the fuel economy, your speed or the performance would be low and the customers would not like it, right? So our end goal is to sell these cars to customers, and we have to get the customers to like the cars. So that's why we always use the optimization. We never use the word maximize. It's because the attributes has to be optimized, but we can't think of like one attributes and like make it the best. So, okay, let's go to the diagram again. So we have these calibration tables, and then when we start the model-based calibration optimization, first we have to design a DOE. DOE is like design of experiment. It's nothing other than like initial set of values for these calibration tables. And then we run those calibrations or like those models with those calibration in a computing cluster. Indika, could you press like back button twice, backspace twice? I need to get those images out, even the brain. Thank you. All right. So now we get those calibration tables into the model, the DOE, and we run those models in a cluster computing environment. So these models are high fidelity. It takes time to run them. And as we mentioned earlier, we need to run millions of simulations to come up with the like optimized number. So we can't run them sequentially, which means like we can't finish one simulation and then go to the next one, and then it's very like time consuming. So we have to run these models in a cluster computing environment in parallel. So right now we have the capability to run like 512 jobs in parallel in our cluster. And once the first iteration is finished, we get the results, we post-process the results, and we calculate our objective or the cost function. So it could be, as I mentioned, it could be the fuel economy or 0 to 100 kph time or whatever that you need to optimize. And then comes the machine learning algorithms. We use in our team, we use genetic algorithms, but there are like other avenues that you could use. But here we use genetic algorithms. So we feed the results to the genetic algorithm, which is the brain of the system, right? So now genetic algorithms look at the objective functions or the cost function. Now it changed the cal table. Now here comes the machine learning. It tries to learn like how to change them. So we couple the cal table with the machine learning algorithms to the intermediate functions. And then from there onwards, the machine learning algorithms takes on the process, and it changes the calibration tables, and then it runs simulation in the cluster again. So this process is repeated iteratively until we reached our budget, because these are not like cheap simulations. To run this one, we have to run about like 6,000 computing hours. So in a cluster environment, so we have to spend money for that. So we have a budget for these studies or like time limit. Someone would come and tell us like, I need these results in 3 days. So then that's my time limit, right? And then we have a budget, like it would be like $10,000 per study, or like let's say $5,000 per study. So then everything comes down to the like time and money. So we run these studies like either until our budget is consumed or like time is reached. So then we finish that and we collect the results and we select the best design out of that. So let's talk about like how we select the design. Indika, could you go to the next slide? Okay, so this is an actual example we did. So we select our design using a design selection methodology called multi-criteria decision analysis, or as Pareto. So this is one of the techniques that we use to select our design. So in this study, we optimize our vehicle for three objectives. So it's called the multi-objective design optimization problem. So it's to maximize the fuel economy for 3 cycles. So here we have EPA, stands for Environmental Protection Agency. So that agency, that's a government agency, comes and dictates the minimum fuel economy standards that we have to have in the vehicle. So we have like 2 different standards that we measure the fuel economy. One is called the city and the other one is called highway. So city is like, as name implies, when you drive with high traffic area, especially like, let's say in Colombo area, right? So that's the fuel economy you get for like your city driving. And if you go like a little bit outstation, or like, let's say in Express 1 highway, so you have a different kind of fuel economy. We call it highway fuel economy. And we have like minimum standard to meet for these kind of like driving conditions. And then we have to present the combined fuel economy. So in the actual vehicle tuning, or like calibration optimization, if you tune the calibration to have a higher city fuel economy, your highway fuel economy goes down. So these are like competing objectives. So in this study, we look at like 3 competing objectives, actually 2. So that is city and highway fuel economy. So in order to tune these parameters, or like get these different attributes optimized, we have design variables. So as we discussed, we call those tunable parameters energy management calibration tables. So to optimize this, we used a genetic algorithm called AMOGA. In longer term, it's called Adaptive Range Multi-Objective Genetic Algorithm. So that's the algorithm that we used. So on the top right-hand corner, you can see 2 tables. So that's the blue one is the base table. The first table that we started with, that's our DOE. So that's the table we started with. And then the red one is one of the calibration tables that genetic algorithms optimized for us. This AMOGA algorithm came up with this table. And in the bottom right-hand corner, you see like a nice dot graph. So each dot here is a design. We call it a design. So that is a different combination of calibration, right? So now let's say we discussed like we have 10,000 plus calibrations. So we can like change those calibration to have like infinite number of combinations. So each dot is a design. We had to limit this study for like 10,000 designs. You see like 10,000 dots here. Each dot represents a design. So on the x-axis, you have the city fuel economy. I think I name it as hot FTP. So that's another name for city. And on the y-axis, you see the highway fuel economy, right? So these black lines on the graph are the baseline or what we started with. So as you can see, anything on the top right-hand quadrant is a design that improves both highway fuel economy and the city fuel economy, right? So it's above or like beyond the highway and the city fuel economy. So that's a good design for in terms of the highway and the city fuel economy. And in terms of the color, we represent the combined fuel economy. So baseline combined fuel economy is represented by the color orange, but we have only one color above that, which is red. So if we can find a red dot in the top right-hand quadrant, so that's going to be our design. So right now, Indika is pointed to that design that we selected. So that design gives us the best or like the optimum city, highway, and the combined fuel economy. So this is one of the criteria that we use to select our designs. So this is called multi-criteria decision analysis, or the Pareto front. Indika, let's go to the next slide. Okay, now let's talk about the bigger picture, why we do that, right? So we constantly talk about topics like the machine learning algorithms replaces human engineers or like humans in the near future. So this is actually not replacing human engineers, but in our example, the machine learning algorithms helps human engineers to do their work efficiently and effectively. So in a typical prototype vehicle or the test vehicle based development, what a calibration engineer would do is like they would use their computing resources and they would study the calibration patterns or like combinations, and they would use some hardware tools. We use ATI Vision, so that's like a product name. So we use ATI Vision and upload those calibration into a test vehicle. So you can see these camouflaged or like black dot vehicles. So those are called development vehicles. So we upload those calibration into these vehicles, and then behind at the back of this like picture, you can see one of our test labs. It's called the it's a test lab. So we run this vehicle in the test lab. So that's the traditional approach. Indika, could you click one? Okay, so the problem with this approach is the design validation time. If you are the calibration engineers, you have to spend like hours and hours on coming up with these calibration combinations. And at the same time, these calibration combinations are becoming complex because the vehicles are becoming complex. So, and there are like multiple of those calibration tables that you need to optimize. And when there are like more tests to be done, you need more prototypes and you need test lab times. So even these prototypes, as Indika mentioned, to produce the vehicle before the actual production vehicle, it's in the range of like kind of like $500,000, like $500,000. So if you need 100 of them, you can imagine the cost for the product development, right? And running the lab is not easy because you have to run this lab in as a controlled environment. So you have to maintain the like humidity, temperature, and all these things. So it's really expensive. So this process is becoming more and more expensive. That is where we came in and try to help these calibration engineers or like Ford Motor Company in general to reduce some of these costs. Indika, could you please press? Okay. So now we used a machine learning algorithm to replace, not replace, to help the calibration engineers. I would not use the word replace because we are not replacing, we are just helping calibration engineers. I have to be really careful about that. So the machine learning algorithm right here takes place like the calibration engineer's role, and it now decides how to change the calibration engineers. Now everything happens in a computer. It doesn't need all these hardware tools. Now it all trickles down to 1 and 0 decimal like binary numbers, and it changed the calibration or the like calibration algorithmically. Now instead of the test lab and like a prototype, we use the computing cluster and a CAE model, right? So we run those simulations in a computing cluster. So that is kind of like the bigger picture that we want to achieve. Indika, could you please enter one more time, Dr. Wijayasinghe? Thank you. So the whole effort, the goal of this effort is the product development or the design validation efficiency. The efficiency comes in terms of two things. The first one is the time, design validation or like product development time, and the cost. So that is really important. As Indika mentioned at the very beginning, so now we are in a global market, right? So our product goes to North America, South America, Europe, China. I think some of the products are now coming to Sri Lanka too, right? So we have to like come up with this product kind of like in a very short time period. The competition is now global. It's not like content to North America or like Europe, but it's a global competition. And there are like many players in the market. So and also like as Indika mentioned, the customer's expectations. So we can't just think about ourselves, because as customers, you would go to the like Ford showroom, or like you would go to the like even to like Tesla dealer. So you would go to like Toyota dealer and you would compare like all these vehicles, right? So you are educated. So we have to make this product development process very efficient. So that's the bigger picture of this whole process, right? So that everything comes down to like the time and money. All right, Indika, we can go to the next slide. Oh, all right. I think we are at the end of this technical presentation. So even though Dr. Wijayasinghe and myself talk about these things, so this is not like something that Dr. Wijayasinghe and I did by ourselves. So there are 100 odd engineers involved in this effort. Specifically, this is our team. So it's called the model-based calibration optimization team. We have like 14 excellent team members coming from all over the world. So working together. So these are like name lists. I'm not going to go through like each and every name, but it's a very diverse team, like different backgrounds, like all over the world, but it's like a family. So the reason that we included this photo at the bottom is like, we do a lot of things like for the fun activities. So this is when like this was before COVID. So when we went for like lunch outing. So we do all these things. So team dynamics is equally important. So it's like very wonderful team. I would like to thank each and every member for their contribution for this team. Indika, could you go to the next slide? All right. So I would finish this slide and then we will come to the Q&A session. So now let's talk about higher studies or the career opportunities in America. So this is specifically in United States, even though we say America. So this is how this is the path that Indika and I followed to be here today. So as you all know, we finished our undergraduate from University of Peradeniya in different departments, but then we entered into the into grad school or the graduate school in America, and then like we followed different paths, but ended up in the same place. So if you want to follow the same path, so the entry requirement for the graduate school is like, first you have to have a bachelor's degree. So that degree has to be like 4 years. For you guys, there's no problem, right? If you have a 3-year general degree, it's very impossible. It's very like hard to get into a master's or PhD program in US because the requirement is you have to have like 4 years of undergraduate degree. And the next is like you have to have an English language requirement. Predominantly, it's TOEFL, and like some universities accept IELTS results too. But if you haven't decided yet, we highly recommend you to take TOEFL. With TOEFL, you have like higher opportunities than the IELTS. Then you have to finish the graduate recording exams or the GRE. So that's like a must for most graduate schools. So you have to have a minimum score for the graduate school. So it depends. So we don't know the exact number because it depends from school to school. And then but the requirement is like you have to have that. You have to maintain a good GPA. I can't tell that it should be 4.0 or like 3.5. So the selection committee decides whether to admit you or like not to admit you based on the combination of these requirements, right? So even though you have 3.0, so don't think like you don't have a possibility to get into the graduate school. You have. It depends on the other factors too, right? It's always better to have a good GPA as in a general term, but if you have it, you don't have like a set cutoff number for the GPA. Then you have to have official transcript. So it's very easy to obtain from the registrar. And then the other thing is other two most important things are like the letters of recommendation. So your faculty or your lecturers or professors would write these letters of recommendations. Even though you don't think, some might not think like it's very important, the letters of recommendations are really important. People actually read them, right? So then make sure that you have like good networking with your faculty or like professors, and then you have like probably you need like 3 or 4 letters of recommendation. So you have someone like some faculty or like professor who's willing to write a good letter of recommendation for you. At last but not least, so you have to write a statement of purpose, or it's called the personal statement. This is about you, right? So what you have done so far and like where you want to go from here. So it has to convince the selection committee of solid past achievement that shows that like you are willing to succeed in the graduate school, right? So those are the entry requirements for like higher studies or the graduate school in USA. In terms of funding, usually you don't have to pay for studies, right? This grad school or like especially if you are in a PhD program, right? In master's program, sometimes you have to pay, but even for the master's program, you have these funding options available. So you can get the funding as a TA or like teaching assistant. In that case, you'll be teaching classes or like assisting another professor who's teaching a classes for tutor marking and like delivering homeworks and proctoring exams, all these things. So you are paid a stipend for these things. So which usually like it's enough to cover your tuitions and then like other expenses. Then the other method is like if you're a professor, usually you have to select a professor to do your grad studies, to do your research. So if you're a professor or your PI has enough funding for the research, he might fund you with the research assistantship. If you have a research assistantship, your expectations is to engage in research and then like come up with the results. So you might get a stipend from a research assistantship if your professor has enough funding for that research. Also like you might get scholarships and fellowships. So you have to apply for these scholarships and fellowships. So you have to read about, excuse me, you have to read about university website, and then they will list what are the scholarships and the fellowships available for you. And then you have to prepare a like application packet and apply for these scholarships and fellowships. And they also like coming a good source of funding. In terms of like what happens after graduation, so immediately after graduation, you can get a visa called optional practical training visa. That visa is initially granted for 1 year, but you can extend it for 2 years if you meet certain conditions. So the requirement is like you have to work in a job which is related to your field of specialization. So if you are an engineer or like especially electrical engineer or mechanical engineer, your job has to be in like one of these fields. You can't just work in McDonald's and say like, I need to work here for 1 year or like another 2 years. It has to be related to your field of specialization. So after that OPT visa time, usually your company or like your employer would apply for a work visa. Those visa categories are called H1 and O1, and they can extend up to 6 years. During that time, you can apply for green card, and hence from there you can apply for the citizenship here in US. So in terms of the career, you can select academic careers or industry careers, or you can craft your own career. So in terms of the academic career, usually like the least resistive path is like go into a postdoctoral fellowship, and that's what Indika and I both did like before we changed our mind to join the industry. So you can do a postdoctoral fellowship under like a good PI, and then you can become an assistant professor. From there you will be tenured into associate professor, and from there to a full professor. So that is the university career, or you can join a national lab or research lab to pursue your academic career. If you want to come into the industry, so you can join the industry as a research engineer, and then you have the career path to be a technical specialist or supervisor or manager. Like it's limitless possibilities. You can become like whoever you want if you have the aspirations. Or else, if you want to be like purely research side in the industry, so you can join the industry as a research scientist and become a principal research scientist. So it's all like what you want to do after that. Third option, it's not like, it's not last but not least, right? So you can craft your own career. So if you have like aspirations and willingness and like willingness to take risk and stress, so you can like start a startup. So that's your own company. You define the your destination. If it is not a technical startup, you can start other business ventures, right? So here, actually in USA, people are really supportive of these startups and business. So it's very, I would say, doing business index is very high here. It's very easy to do business in US. And then from there, like you have limitless possibilities. Like it's not limited to anything, but you can do like I would not say like whatever you want, but like you can do a lot of things, right? So you have like limitless paths to carry on from here. I think with that we come to the end of the presentation, Indika. Okay, one more slide. So life in graduate school, I would say, if you are thinking, is not boring. So this is like one thing that we did. So it's traveling. I know, like when we talk about like boring or not, traveling might not be the most exciting thing to some of you, but like we thought like it would be cool to include this slide. So this is a road trip that we did in US. We covered this road trip, I think, in 11 days. So that was about like 8,000 miles in like 11 days. So these are like kind of like exciting things that you could do. Not the most exciting things, but what we included this slide here to tell you that the life in graduate school is not boring. So in the bottom right hand side picture, you can see like we took a picture when we were at Yellowstone National Park while we were on this road trip. So on the right hand side, you see Dr. Wijayasinghe, and wearing this black t-shirt is me. And on the left hand side, I'm pretty sure you can recognize that person. That is no one other than Dr. Parakrama Ekanayaka. So we were in grad school together and we did like all kind of these things, right? So, but this is only like something to tell you that life in grad school is not boring. You have like free time, so you can decide like what you do and what is exciting to you. So you can plan your like on time, and like it's very exciting. So
This is exactly like 10 years ago, like almost exactly August 2011.
Yes, this is 10 years ago, right? Exactly. So one thing I would like to add, like we included only 2 short slides here for the higher studies in USA. So few of like our friends, we are putting together a forum to discuss about these things in detail. So once we finalize that forum, it could be like discussion sessions or the panel discussions like this. So we will let you know the link. If you are interested, you can just participate in those discussions, and we will help you to like get a kickstart for those for like graduate school or like higher studies in USA. I think with that, we come to the end of our presentation.